So let's talk about vectors that are equal and vectors that are opposite. So when you talk about numbers being equal, it's very simple to distinguish they're equal, right? If you have 3, then if you can identify some other number as also 3, we see they're equal. With vectors though, you can't just have, right, the size of the vector being equal, right? These two are, let's say they're the exact same length, they're not equal because they have different direction, right? The only vector that will be equal to this one, right, will be this. I just noticed, just copy and pasted that. I put it right beside, and it's exactly the same length, and it's facing, right? The arrows are going in the exact same direction. In fact, they're parallel, right? They're parallel. Now, this vector doesn't have to overlap this, right? It can be here, it can be here, it can be here. In fact, if I copy and paste a bunch of them here, right? And let's label this A, B, C, D, E, F, G, H, right? They're all equal. Okay, as long as they have the same size and same direction, right? So if I had a vector that looked like this, right? And here it is again. If you have, let's call this A, B, C, D. Also here we can say A, B, same size and same direction. Okay, in fact, they have to be, if you were to give an angle here, this angle has to be exactly the same to the horizontal. Then we can say AB is equal to, right, CD. Okay, so what does that mean to be equal, right? There are some things, some neat things we can do with when we add them and subtract them later. For example, if I have AB plus CD, right, what happens to normal numbers if you're to add the same numbers? Well, we can say we just have 2 of those numbers, right? Maybe 2 is not a good example here. Let's say you have 5 plus 5. We can say this is double of 5. And you can do the same thing here. This is double of AB. We can say that, okay? Let's now talk about, okay, opposite vectors. Opposite vectors. So opposite integers, opposite numbers. For example, if you were to have 3 and subtract a 3 or add a negative 3, we get 0. Okay, they cancel each other out. And same thing happens to vectors. If I had a vector like this, right, what would be the opposite vector? It will be this, exact same magnitude, okay, but the direction is in the opposite direction. So AB, and let's say CD. Okay, AB is clearly not equal to CD. They're not the same vector. But, right, we know that if you were to add these two, okay, if we were to add these two, we should get 0. And we say 0 vector, okay, to say it's a vector with no direction and 0 quantity. So then what happens is, well, if I just do some algebra here, AB then is equal to 0 vector subtract CD. Okay, 0 vector by definition, it does nothing when you add or subtract to another vector. So what we get here is AB is equal to the negative of CD. Okay, the negative of CD. Okay, and note that this convention of having a tail and a head, to say start from the tail to go to head, right? This would equal to, also, if you switch the head and tail location, so AB is this way, then BA will be this way. So if I actually multiply this vector by a negative, they would also equal to each other. This means, so start from B, go to A, but if you multiply a negative, what it does essentially is to change the direction back to AB. Okay, so AB is equal to not BA, but negative of BA, because negative changes the direction, change the position of the tail and the head. summary, opposite vectors, right? Opposite vectors, okay, has same magnitude. The magnitude does not change, but what it does have is opposite direction. And it's usually denoted by a negative or changing the head and tail, right? Head and tail location.